Okay, let me explain what we have here and what we're going to do. Up here we have a pair of charges which I've given names. Call the first one Q1, the second one Q2. Notice that Q2 is 4 times bigger in magnitude than Q1. Down here we have a floating free third charge, Q3, which is a positive 1. That means that this charge here is equal in magnitude to that charge there, but opposite in sign. Now, what I want you to do is to take this charge and put it in a location where the net force on it due to the other two charges will be 0. In other words, this is some place you can put it where it won't move because it will be in force equilibrium. And for that question, I give you 4 locations. In other words, whoops, messed up. Okay, got it fixed. Here's the floating charge. You can put it at A, B, C, D, E, F, or G. And which location is closest to the probable location at which the sum of the forces on Q3 due to Q1 and Q2 will be 0. So go ahead and answer that question. Okay, hopefully you chose position C. And the reason it's position C is because Q1 will attract Q3, and so there'll be a force in this direction of attraction. Q2 will attract Q3, so there'll be a force in this direction due to the attraction. If I draw those vectors in, this would be the force of attraction by Q1. This would be the force of attraction by Q2 on Q3, and you see they're equal and opposite. And why are they equal and opposite? Well, you see Q3, it has to be closer to the smaller charge because this is a bigger charge. And since this is 4 times bigger, it needs to be twice as far away from Q2 as it is from Q1, right? Because of the inverse square law. Because twice as far away means the force is 4 times weaker, but the charge is 4 times bigger, and so it cancels out perfectly. So that's the location where the sum of the forces on Q3 is going to be 0. Okay, let's try that again. Here's a Q4, another little charge, only this charge is negative. So of the 7 choices, where are you going to place Q4 such that the net force due to the other 2 charges is 0? And for this exercise, you can imagine that Q3 has been removed. It's not there. So we have Q1, Q2, and Q4, and consider Q3 gone. Okay, I hope you, correctly chose that it goes to the same position, position C. And although the charge is opposite, Q1 will now repel that charge Q4. So the force will be in that direction. But Q2 will repel Q4 in that direction. And for the same reasons that we had last time, those 2 forces, the force of 1 on 4 and the force of 2 on 4, will be equal and opposite, and the net force will be 0. Okay, here's the third floating charge. Here's a third floating charge, and assuming that we get rid of Q3 and Q4, the thing is blank, we have Q1, Q2, and Q5. Where are we going to put Q5 so the sum of the forces is 0? So here's hoping you correctly realize that Q5 goes in the very same position as we put Q3, Q4, and for the very same reasons. In this case, since it's positive, Q1 would be attracting Q5, and since Q1 is bigger, the attraction would be twice as big. But the attraction to Q2 would also be twice as big, and so once again, the force on Q5 from Q1 and Q2 is going to be equal and opposite, and the sum of the forces will be 0. So noticing that no matter what the charge, no matter what the magnitude of the charge or the sign of the charge, the location where the sum of the forces is 0 is the same location, and that's because that's the location where the electric field due to Q1 and Q2 is equal to 0. Remembering the electric field is the electric force per unit charge. It's independent of the charge we put there. So if this is the location where the electric field is 0, no matter what charge, magnitude or sign you put there, the electric force is going to be 0, because you can see from this equation that the force on any charge is going to be the magnitude of that charge, Q3, Q4, or Q5, times the electric field at that point. And if the electric field is 0, then the force will be 0. Okay, let's run through the same exercise again. In this case, Q1 is 4 positive charges, Q2 is 1 negative charge, and our floating Q3 is a single positive charge. Where are you going to put that? So the sum of the forces on Q3 is 0. I hope you correctly chose position G. And why is that? Because Q1 is going to repel Q3, so force in that direction, and Q2 is going to attract it. And if we get the position right, they're going to be equal. So what do we need? Remember from the last problem, this charge is 4 times bigger. So because of the inverse square law, we need to be twice as far away. Twice as far away means that that force is 4 times weaker than that force. Let me draw the vectors in. So this is the force of 2. Whoops. On 3, and I'm going to go off the screen, but this is the force of 1 on 3. Let me see if I can move this. There, that's better. I lost A, but that's okay. Let's go back to the pen. So these two forces, once again, just pay attention. This force is what? It's the force of repulsion of Q1 on Q3. And this force is what? It's the force of attraction of Q2 for Q3. And they're balanced because the distance counteracts the difference in charge exactly. Okay, where are you going to put Q4? Figure it out. All right, I hope you correctly put Q4 in the same place for the same reasons. The force of 1 attracting will be equal to the force of 2 repelling, because the charge ratio is 4 to 1, and the distance ratio is, this distance is twice as close as that distance. So that makes this force 4 times bigger, accounting for the fact that the charge is 4 times smaller. And once again, the sum of the forces is 0. And so, finally, I give you a Q5, which is twice as big as Q3, And where are you going to place the Q5? No surprise. It goes at G again. And the reasoning is the same. The forces will be twice as big, but they'll still cancel. And so the location is the same for all three, because that is the location where the electric field due to the charges Q1 and Q2 is equal to 0.